Hello and welcome to our first online lecture. We are going to begin this semester with chapters 2.1 and 2.2, an introduction to sets. We'll start off with some definitions. A set is any collection of objects. A well-defined set is specified in such a way that we can tell whether any object is or is not in the collection. Each item in the set is called a member or an element of the set. And sets are always denoted by capital letters such as A, B, or C. And then some notation that we'll be using. The first one, you read it as A is an element of A. So this little kind of E-looking guy means element. Elements of sets generally are denoted by small letters or lowercase letters, while the set itself is denoted by the capital letter. The second one, with the cross, the E with the cross through, is going to be A is not an element of A. And then lastly, this is the symbol for the empty set. The empty set is kind of what it sounds like. It is a set with no elements. It is just an empty set. When we're representing sets, a set is described by either listing all elements between braces or enclosing a rule between such braces. So an example of a rule would be the second bullet point here. So A equals, and then we have the braces. It's read as X such that X is less than or equal to 10. So this line here is such that, and then this is the rule. So if we wanted to list out this set by the description method rather than the rule, we could say A equals, and we could have 10, 9, 8, 7, 6, 5, and so on and so forth, however far we want to go. Another example of a set could be A equals X such that 0 is less than X is less than 5. This set can also be written by the descriptive method, which would be A equals 1, 2, 3, or 4. And the reason that we don't include 5 is because it's strictly less than and not less than or equal to. So 5 is not in this. 5 is not an element of A. However, 1 is an element of A, 2 is an element of A, 3 is an element of A, and 4 is an element of A. There are lots of things that wouldn't be elements of A if we're looking at all the numbers. We could also use 0. We could say 0 is not an element of A. We could say 10 is not an element of A, etc. Next, we'll talk about cardinality. So the cardinal number of a set is the number of elements in the set. For set A, the symbol of cardinality is in and then parentheses A. It's read in of A. You can think about it as just the number of elements in A, as the definition says. A set is called finite if it has no elements or has a cardinality that is a natural number. If a set is not finite, it is called an infinite set. So some examples. So let's use the example that we were talking about here. If we have A is equal to 1, 2, 3, 4, then the cardinality of A is 4 because there are 4 elements in the set A. If we have And then also A would be a finite set because it's a natural number. We could also think about if you have a set, let's call it B, and it's equal to X such that 0 is less than or equal to X is less than 100. Okay? How many elements are in B? Well, we'll start at the number 0 and we go all the way to 99 since we're not going to include 100. So we're including numbers 1 through 99 and we're also including 0. That means the number of elements in B would be 100 because you have to count the number 0 as an element. Does that make sense? Also a finite set. Let's consider a third set. Let's say we have the set of all x's such that x is a real number. So I'm using a lot of notation here. So we know that this vertical line is such that. We know that this little e is element. And if you haven't seen this big R before, the double R means real number. Real numbers go from negative infinity to positive infinity. They cover decimals, fractions, all the numbers that we're used to dealing with, right? So this set would be infinite. Because the real numbers are an infinite set. Other sets that are also infinite would be stuff like the integers, which is represented by a big Z, or the natural numbers, which is represented by the double N. The universal set is a set of all objects in the universe. The universal set is denoted U. So whatever universe we're living in will always be stated. For example, if we are living in the universe of numbers 1 through 10, then all my other sets will be contained inside of our universe. For example, I could have a set A be four, 5, 6, 7, 8, 9, and it is contained in the universe. If you'd like to see this as a picture, we always draw a box to show we're inside of our universe. And then the set A would be inside of this box. So A is 4, 5, 6, 7, 8, 9. And then everything else lives out here in the universe. So 10, 1, 2, 3. You can also just think of the universal set as a big set, or I like to think of it as where we're living. So right now we're living between 1 and 10, but we're focused on this set A, which is 4 through 9. Complements and disjoint sets. If sets A and B have no members in common, we call these sets disjoint. And we say that their intersection is empty. So this upside down U here means intersect. A intersect B is empty, means they have nothing in common, nothing in their intersection. For example, if I had A equal to 1, 2, 3, and B equal to 4, 5, 6, they have no members in common. Not one member is the same. So you can say A intersect B is empty, or you can say A and B are disjoint. Right? The complement of a set A is relative to its universal set U, and is denoted A with this little tick mark up here, A complement. It is the set of all elements not in A. The notation is A complement equals X such that X is in U, our universal set, and X is not in A. And then a fun fact, A intersected with its complement is always empty. Let's think about this as an example. Let's say our universal set is 1 through 7. And then we'll use the same A and B as up here at the top of the slide. So that means I have 1, 2, 3, and this is set A. I have 4, 5, 6, this is set B. And they all live inside my universe, which has a 7 because it's in neither A nor B. So A complement are all the numbers that are in U but not in A. So since 1, 2, and 3 are in A, they cannot be in A complement. So A complement is simply the rest of the numbers in U. And then hopefully now you can see that A intersected with A complement will always be empty by the definition of A complement. Let's do some more examples. Let U, our universal set, be V, W, X, Y, and Z. And let A equal W, Y, and Z. And we'll find A complement. Okay, well, A complement is defined as all of the letters in U that are not in A. So that means we'll look at U and we'll compare it to A. So first we see V. V is not in A, so we'll include it in A complement. W is in A, Y is in A, and Z is in A. So that means the only two letters in A complement are going to be V and X. Okay, I'll also draw you a picture. This is my set A. Make that a little bold since we're dealing with letters. So set A is here. Here's my universe. And then out here in the universe will be V and X. Next, we'll look at subsets and set equivalents. If each element of a set A is also an element of set B, we say that A is a subset of B. And then it just should be noted that the empty set is a subset of every set. Let's do an example. So if I have A is equal to 1, 2, and B is equal to 1, 2, 3. Okay? So you can look at these sets and you can see that every single element of A is also included in the set B. So this means that A is a subset of B. B, however, is not a subset of A because A does not contain the number 3. So A is a subset of B, but B is not a subset of A. So next bullet point. If a set A and B have exactly the same elements, then the two sets are said to be equal. And then some notation. This kind of C-looking guy here, he means subset. Equals is still equals, so this is still equals. And then the C with the line through it is not a subset. And then this is still not equals. So in the example that I wrote at the top of the slide, we would say A is a subset of B, but B is not a subset of A. They are also not equal, right? Because they both do not contain that number 3. If you would like to see this in a picture, I could draw a picture too. So I didn't declare a universe, but we'll call the universe just all the numbers. So here's B, right? And then A would be inside of B, so 1, 2. And B would have those 3. And then you will have the other numbers, etc. Okay. Let's do another example. Suppose we have a set A A has the letters X, Y, and Z. So if we want to find all the subsets, we want to find all the subsets of A that could possibly exist. Well, I could have every letter. Okay? The set of only X would be a subset of A. How about the set of only Y? That one works too. Then I could also have this set of only Z. So sets with one single element, all of these are subsets of A. Now let's do the 2 elements, X, Y. I can have X, Z, and I can have YZ. The other thing I can have is the set itself. XYZ. Because this set here, XYZ, is a subset of A because all of its elements are in A. Even though it is the same set, we would still count it. Did I get all of the subsets? Let's think about it. I got each individual letter, then I did the pairs of 2's, and then I did the whole set. However, I am still missing a subset. Which one am I missing? Well, if we scroll back up here, it should be noted that the empty set is a subset of every set. So I'm actually missing the empty set when I'm listing out all of my subsets. Now I have all my subsets since I've listed the empty set. So there are 8 subsets of set A. Let's do another one. So let B equal the set of cats and dogs. B is just the set of cats and dogs. Since a set can be a collection of any objects, I can also use living creatures. It doesn't always have to be numbers and letters. So we'll look at the set of cats and dogs. Let's find all the subsets. Okay, I'll do the single sets first. So the set of cats is a subset of set B. The set of dogs is a subset of set B, as well as the set itself, cats and dogs. And last but not least, we can never forget the empty set. All right, moving on. The difference of two sets. The difference of two sets A and B is defined by A minus B equals X such that X is in A but not in B. If it were B minus A, it would be X is in B but not in A. So you're taking away the set that looks like it's being subtracted. So, for example, let's say my set A is equal to W, X, Y, Z. And my set B is equal to W, Y. Then A without B is going to be everything that is in A, but not in B. So that means I will only have X and Z. So you take away the elements that are in common. Let's do an example with the numbers. Let's use C and D for our next two sets. Let's say C is equal to 1, 2, 3, 4, 5. And D is equal to 3, 4, 5, 6. So I want C without D. So I want none of the elements in D to be in this set. So I have only 1 and 2. Because 3, 4, and 5 are also in D. However, if we did D without C, so now I want all of the elements in D that are not in C. That gives me only the number 6, because again, 3, 4, and 5 are in both C and D. This concludes our first lecture. Thank you for listening, and I hope you have a wonderful rest of the day.